Right, our next speaker is Takato Otsuka. He's from the University of Electro-Communications, and he is presenting Haskell library for safer virtual machine introspection. Please take it away, Otsuka.
Thank you. I'm Takato Otsuka from the University of Electro-Communications in Japan. And this talk, the title of this talk is Haskell library for safer virtual machine introspection. And this work, this is a joint work with Iwasaki. So let's begin. This research is concerned with a technique called virtual machine introspection, also as VMI. VMI is for inspecting the guest OS in the virtual machine from the VMI program on host OS by accessing the guest OS memory. For instance, the VMI program can scan the guest OS for a hidden process and can kill the process from the outside. By inspecting the guest OS in this way from the outside, the obtained information is highly reliable even if the guest OS is infected by malwares. However, VMI programs should appropriately interpret the hardware-level raw data as concrete data structures in the guest OS. For example, if the obtained information is a bit pattern of Windows 64, the VMI program should interpret them as a 64-bit signed integer. For a concrete example of VMI program, we present a program that obtains a process ID in the Linux guest OS by using LibVMI library. For the first, in the Linux guest OS, the process ID is located in the member PID, which is a 32-bit signed integer type in the task structures. And task structure is also exists statically in the kernel as a init task variable. Therefore, the VMI program can read the process ID by accessing the member PID in the task structure from the init task variable. So this slide shows a C program that directly uses LibVMI library. And there are three parts in this program. Initialization part and finalization part and main part. So let me talk about main part. The main part consists with 4 steps to retrieve the process ID. So in the first step, it obtains the address of the variable init task by calling the LibVMI's API. Similarly, the offset of the member PID can be obtained by another LibVMI API. Then, in the third step, the program calculates the sum of the address and offset in prior steps and obtain the PID's address. Finally, in the last step, it reads 32-bit data at the address of PID to obtain the init task's PID. Through the program in the previous slides, I want to point out 2 serious problems in using LibVMI. The first one is reading and writing guest OS data requires complicated procedures. As seen in the previous slide, it is necessary to calculate the address of a structure member and use an appropriate API for the bit width of the member value, in this case, member PID. The another problem is that statically undetected, but fatal errors can occur easily. There are 3 categories for possible errors. The first one, which we call C1, is specifying an incorrect variable symbol name and structure name and member name. For instance, the tasks underscore struct is misspelled as task struct, which the underscore character is missing. The second one, C2, is making a mistake in address calculation. In this case, it subtracts the offset, which it should be added to the address of top structure top. The last one, C3, is using an API with bit width other than that of the target data types. For the member PID, the bit width other than 32 is incorrect. These 2 problems requires carefulness on the programmer, and it also puts an enormous burden on the programmer. In addition, such 3 categories of errors might induce retrieving false data on read operation, or in the worst case, a crash of the guest OS. To solve this situation, this research aims to alleviate 2 problems from the viewpoint of programming language by using 2 approaches. One is that utilizing the static type checking mechanism to detect the programmer's errors at compile time. The another is to employ metaprogramming to make it easy to develop VMI programs. To support these 2 approaches, we adopt Haskell and create a library named HaVMI. This slide shows the Haskell program that obtains a process ID in the Linux guest OS in terms of HaVMI. The parts within parentheses generate parentheses use metaprogramming, and it generates dedicated types and accessors at compile time for reading the process ID safely. For instance, the generate struct meta function takes the structure name and member's name to generate dedicated types and accessors for the member PID. This blue rectangle shows the generated code by generate struct meta function. Also, the generate symbol meta function generates takes the symbol name and to generate the corresponding accessors for the variable init task. In this case, get init task. For intuitive use for programmers, the get symbol meta function takes the symbol name to generate a corresponding Haskell variable, in this case, get init task. And the right star arrow operator generates a snippet of code that reads the member PID in the task structure. These meta functions and meta operators are explained later in this talk. In addition to the generating codes for accessors and types, this program merges the 3 steps from obtaining the offset of the member PID to read its in a 32-bit into which takes 5 lines in the case of C program into a single line, as in this line. So before looking at code generation in HaVMI, I explained the generated types and accessors in HaVMI. First of all, the HaVMI uses data types to represent pointers and values in the guest OS. Each data type for the pointer wraps the address of its pointer, and the data types for values wraps its data. By using these data types, Haskell's type checking mechanism can statically detect every type mismatch of address and value. For the variables in the guest OS, HaVMI provides them as Haskell variables, as in this getInit task. And then, having declared the data types in the previous slide, HaVMI defines functions that go back and forth between a structure pointer and its member pointer. And by providing these two functions, the programmer need not write address calculation code. It's in their programs. Also, read and write operations are declared as class methods. And the programmer also need to specify the exact bit width, since the bit width is embedded in the instance declarations of that class methods. Next, I explain the meta functions in the HaVMI. Two meta functions generate types and accessors. The first one, the generate struct, takes a structure name and a list of member names, and generates data types and functions and instance declarations for accessing the specified members. The generate symbol resembles generate struct, but it generates variables instead of functions. These two meta functions report an error if a member or variable symbol does not exist in the guest OS. And as seen in the two usage of meta functions, HaVMI does not generate code for all members and variable symbols. This is our design choice, so I will discuss it later. So, in addition, HaVMI provides meta operators that go back and forth between a structure and its member. The right arrow operator obtains a member pointer from a structure pointer, and the left arrow does the opposite. And in these two meta operators, it generates a corresponding function name, this case PID of or PID to task struct, from the specified structure and member name. In addition, these three meta operators that expand to multiple procedures are available. The first one, right star arrow operator, calls the right arrow operator, and then reads the value at the obtained member pointer. Next, the double double arrow operator takes a list of members instead of a single member, and it generates an appropriate sequence of the right arrow and right star arrow operator for the specified member list, and finally obtains the member pointer to the last member. Lastly, double star arrow operator resembles double arrow operator, but it finally obtains the member value of the last member. In the last, HaVMI provides a meta function that converts a variable symbol name into a Haskell variable. This is a get symbol meta function which takes a variable symbol, and it generates the corresponding Haskell variable get init task from the specified variable symbol. By providing these meta functions and meta operators in prior slice, the programmer need not directly use the generate types and accessors in their programs. Based on the design in the prior slice, I'm going to show how HaVMI statically detects the errors in LibVMI. For a C1-like error, this task underscore struct is misspelled as task struct, which the underscore character is missing. For this type of error, the generate struct meta function signals an error that notifies the absence of such structure, as in here error message. And for C2-like error, in this case, it obtains a structure pointer from the member pointer, whose the direction should be inverted. This type of error was detected by the Haskell compiler, since it is a mismatch between argument type of the generated function by the splice in here, which has a type of PID of task struct, and the type of init task, which is a task struct. Lastly, the possible C3-like error is that passing the 32-bit integer to the print8 function, which takes an 8-bit signed integer. This is also detected by the Haskell compiler, since there is a mismatch between the argument type of print8 function, which is int8, and the type of PID val, which is int32. This, as seen in the previous slides, C2 category of errors that miscalculating addresses, and C3 type of errors that using incorrect bit widths cannot occur in HaVMI. This is because the generated types and accessors hide address calculation and bit widths from the source code. As I mentioned it before, HaVMI does not prepare all types and accessors for all data types in the Linux kernel. One of the benefits is that there is no need to include a huge code for numerous structures. In fact, the Linux kernel defines over 10,000 structures and its many members. Another benefit is that the explicit declaration of C names makes HaVMI programs clear and easy to understand. On the other hand, there is a drawback that every HaVMI program should specify every C name accessed from the program. In spite of this drawback, we judged the drawback as not critical and adopted dynamically generative approaches. Based on the design choice in the previous slide, we developed HaVMI in two phases. The first phase is that defining the types and accessors needed to run example programs. In this phase, the types hold C-type information that enables HaVMI to statically detect the use of different type addresses and values. In this phase, the Haskell's static type checking mechanism was quite effective. In that second phase, we provided concise notations for HaVMI programs. The defined meta-functions and meta-operators simplifies program portions that were inconvenient to write in the first phase, and the meta-programming facility by template Haskell was quite practical in this phase. Also, template Haskell helped the building of HaVMI, but there are some difficulties. Difficulties was appeared when we wanted to define a meta operator that took the Haskell variable instead of a structure name, like this. Unfortunately, this is impossible to define because template Haskell does not support querying the type name of local variables. The type name of local variables is essential to define the right arrow operator since it is needed to generate the corresponding function name. So we finally defined the meta operators so as to take a structure name as in here. All right. In this talk, I pointed out the two problems that two problems in an existing virtual machine introspection library. There are two problems here, and these problems are alleviated from the perspective of programming languages. This is done by creating a Haskell library that uses static type checking mechanism and the metaprogramming facility. Also, we implemented programs that coped with the rootkit in the Linux guest OS. If you're interested, please see our paper. That is all for this talk. Thank you for listening.
Questions for Takato?
Last question about the Haskell implementation. I think it's a pretty cool thing that you can generate all of this template Haskell. Helps you in the ways that it has here. But more a question about VMI in general. How does one actually go about identifying the locations of these structures within the guest image, given that don't worry that's too out of scope, but
identify.
Can
I hear what identify means?
So, you were introspecting on data structures within the image of a guest, and it seems to me like that's not necessarily an easy thing to do, and I was wondering in general how that is done. I know that's not to do with your library per se, but if you have any insight there, that'd be interested. It's okay. it's quite all right as well.
Sorry. It means offset and addresses. The address of variable symbol and the offset of the member in the structure was determined by the JSON file, which generated from the debug information of Linux kernel itself. So by querying, by retrieving the offset and address from the JSON file, we can determine we can calculate the address and offset from guest OS.
So it's statically knowable from the kernel image then, I guess is the, yeah, okay.
Yeah.
Cool.
Sorry.
Thanks.
Thank you.
Any more questions, anyone? All right. I think that's it then. Thank you, Takato.